Okay, today we continue with synchronous counter design. Synchronous counters can count up and down and can be designed to produce special purpose count sequences of non-consecutive numbers. So minggu lepas kita dah tengok ripple counter. Ripple counter, for example, for mode 8, we can count 0, 1, 2, 3, 4, 5, 6, 7 and then back to 0, 1, 2, 3, 4, 5, 6, 7 and so on. Meaning that the sequence will be repeated over the time. But for synchronous counter, we can design it to produce non-consecutive numbers counting. For example, 0, 2, 4, 8, 10, and then back to 1. Okay. So a synchronous counter has a common clock signal that controls all flip-flop. Okay. So we try to see the figure. Okay, this is the figure showing a synchronous counter design. One example of synchronous counter design. So you can see we have one common clock. So the input so the clock will be the input for all flip-flops. Okay. So all flip-flop clock inputs are tied directly to the input clock. Jadi semua input yang masuk ke flip-flop ni akan dihubungkan dengan clock signal ni. Okay. So a synchronous counter shown below has a count sequence of non-consecutive number 0, 2, 4, 6. So ini adalah contoh circuit untuk synchronous counter design 0, 2, 4, 6. Okay, never mind. That one we will see later. Okay, how to draw the circuit. But for the first part, okay, we are going to see this one. Synchronous counter design follows a systematic design procedure. The JK flip-flop excitation table, as shown below, describes the input conditions that produce the output state from each individual JK flip-flop. Okay, there's still lagi JK flip-flop. So if the present state is 0, okay, next state will be 0 if J equal to 0 and K can be 0 or 1. So, bila kita letak tanda X ni, K boleh jadi 0 ataupun 1. Okay. So, maksudnya di sini, present state can be is 0. If the present state is 0, next state will be 0 if J equal to 0, K equal to 0 or J equal to 0, K equal to 1. Okay. Maksudnya condition dia sama ada whole ataupun reset. Okay, kedua-duanya akan menghasilkan perubahan, maksudnya present state 0, next state pun 0. Okay, next. If the present state is 1, next state is also 1. So this is caused by J can be 0, K 0 or J can be 1, K equal to 0. Maksudnya 0, 0 ataupun 1, 0. 0, 0 is whole, 1, 0 is set. Okay, so if the present state is 1, next state also 1 when the condition is whole or the condition is the mode. I mean the mode whole or the mode is set. Okay, the third one, the present state is 0, next state is 1. This can occur when J1, K0 or J1, K1. Sama ada toggle or set. Okay, then the fourth one, the fourth row here, present state 1, next state 0. This can occur when okay, X1. X1 means J can be 0 or 1. So either J0, K1 or J1, K1. Okay. If J0, K1, this is reset. If 1, 1, it is toggle. Okay. So this is the basic idea. So when a variable can take any value, either 0 or 1, we can put X. Okay. So this is, we can draw this one. Okay. If 0, 2, 0, we can write it as 0x, okay, based on this excitation table. Then if we have 0 to 1 change, this is 1x. And then if 1 to 1, x0, and then 1 to 0, x1. We can redraw it using this figure. Okay. Okay, next we are going to see how to design a synchronous counter to count the following sequence 0, 1, 2, 3. So these are the steps in designing a synchronous counter. First, draw the transition state diagram showing all possible states. Okay. So the diagram that I shown just now, okay, this is known as state diagram. Okay. So first, when you are given any question, any sequence to be designed, you have to draw the transition state diagram first, and then set up an excitation table by listing the present state and next state sequence. Then third step, for each present state, indicate the input required at each JK to produce the transition to the next state. And then fourth one, design the logic circuit to generate the input required at each JK. Okay, so let's proceed with the example so it will be clearer for you. Okay, for this one, we want to design a synchronous counter which can count 0, 1, 2, 3, 0, 1, 2, 3. Okay, so first we draw the state transition diagram. Okay, so 0 to 1, 1 to 2, 2 to 3, 3 to 0, and so on. The pattern will be repeated. So that is the first step, done already. And then set up the excitation table. Excitation table, this is the excitation table. Okay, this is the basic framework for the excitation table. Okay, let's do it together. Okay, yang ni kita cuba buat sama-sama. Okay. Okay. So first, we have the state transition diagram 0 to 1, 1 to 2, 2 to 3, and then back to 0. Okay, so now I'm going to draw the excitation table. Okay. Previous state, KPS, previous state, then next state. Okay, so the largest number that we are going to present is 3. So we need only 2 bits. 2 bits. Okay. So A, B. So we are going to have 0, 0, 0, 1, 1, 0, then 1, 1. Okay, this is the present state. And then next state. Okay. So actually I'm copying this one. Okay, we have A, B. Okay. Okay. So this is present state just now. So present state we can have 0, 1, 2, 3. Okay. So the same thing here. Okay, present state A, B. Okay. Or it's better if you put it in this way. Oops. Okay. Okay, present state. And then next state. Okay, next state. Okay, this one from 0. 0, previous state 0. Next state will be 1. Okay, then previous state 1. Next state 2. Previous state 2. Next state 3. Then previous state 3. Next state 0. Okay. So I will put here A prime, B prime. Okay, this one 0, we represent it as 0, 0. 1, 0, 1, 0, 1, 2, 1, 0, and then 3, 1, 1. So to represent 1 here, 0, 1. To represent 2, 1, 0. To represent 3, 1, 1, and then 0, 0. Okay, so we have the same thing here. Okay, now we are going to fill in this part. Okay, so we're dealing with JK flip-flop. So since we have 2 bits A and B, so we are going to have 2 JK flip-flop. Okay, 2 JK flip-flops. So we have JA, KA for A variable A, and then JB, KB for variable B. So if you have 3 variables, for example A, B, C, you are going to have 3 flip-flop, meaning that you are going to have JA, KA, JB, KB, JC, KC. Okay, it depends on how many flip-flops you have, and the number of flip-flops depends on how many variables do you have. Okay, so first I'm going to show you this one. Okay, now we have, try to see this one. Okay, A0, A prime 0. Okay, 0 to 0. Apa condition, apa mode yang mengekalkan 0 kepada 0 juga. So sama ada mode whole ataupun mode reset. Okay, so kalau whole, J0, K0. Kalau reset, J0, K1. Okay, so since J can take any value either 0 or 1, we are going to rewrite it as 0x. So I will write here 0x. Okay. Then next one. Okay. Next row. Okay, I'm going to use green. Okay. A0, A prime 1. So apa condition apa mode yang menyebabkan change from 0 to 1? Okay, 0 to 1 either set or toggle. So dia punya value for JK, if set 1 0, if toggle 1 1. Okay, so K can take any value 0 or 1, J 1, so 1x. So we will write 1x here. Okay, next, let's take blue again. Okay, this one, 1 to 1. Okay, 1 to 1. Okay, what mode is it? 1 to 1, it is whole or set. Okay, so if whole, JK is 0 0. If set, 1 0. So J can take any value 0 or 1. We put X, then 0, X 0. And then for the last row, A1, A prime 0. Okay, what mode caused the change from 1 to 0? 1 to 0 either toggle or reset. Okay, so toggle 1 1, reset 0 1. So we can say x1 because j can take any value 1 or 0, k 1, so x1. Okay, so that's how you fill in the excitation table for this sequence. Okay, now let's do for B. Okay, B0, B prime 1, 0 to 1. Okay, 0 to 1. Okay, the same as this one, 0 to 1, set or toggle. So 1, 1 or 1, 0. Okay, so the answer is 1x here. And then this one, 1, 0. 1, 0, reset or toggle. Okay, either 0, 1 or 1, 1. Okay. Okay, so the answer is x1. Then this one 0 to 1 again. 0 to 1 again. 0 to 1. So set or toggle 1, 1 or 1, 0. So this one, wait, set reset 1, 0 or 1, 1. So 1x. Okay, 1x. Is it 1x? 0 to 1. Set reset 1, 0, 1, 0 or 1, 1. So 1x. Okay, 1x. Okay, then the last one from here. Okay, B1 to B prime 0. So 1, 0 is reset. Okay, either 0, 1 or toggle. Okay, 0, 1 or 1, 1. So x1. Okay, so let's compare with the answer here in your slide. Okay, whether we have the same one, 1x, x1, x1, 0x, 1x. Okay, we have the same answer. So that's how you draw the excitation table, the second step in designing the synchronous counter. Okay, the next step is design the logic circuit JA-KA and JB-KB. The excitation table lists 4 J and K inputs, JA, KA, JB, and KB. We must consider each of these as an output from its own logic circuit with inputs from flip-flop A and B. So let's design the circuit for JA. To do this, we need to look at the present states of AB and the output JA. The JA expression can be simplified using Carnot map as shown below. Okay, so from the excitation table, okay, we have the excitation table for JA. Okay, the same thing that we have done here for JA only. So JA, okay, we draw for JA. Okay, for JA 01XX, do we have the same thing here? Okay, 01XX. So we are going to plot for JA. Okay, for JA we are going to consider. Okay, recall back the Carnot map method that we learned previously. So JA, okay, for JA, we are going to look at the output JA with value 1 and x. We are going to plot output 1 and x. Okay, for output 1, A bar dot B. Okay, 1 and then A B bar x, A B x. Okay, then we draw the loop. So JA equal to B. Okay, next, the same thing we are going to draw for KA. For KA, KA, we have A bar, B bar, X, A bar, B bar, X, A bar, B, A bar, A bar, B also X, A bar, B, X, and then next one is AB. AB is 1. Okay, AB 1. So we draw the loop. So KA equal to B. Then the same thing for JB. For JB, okay, we have A bar, B bar, then A, B bar, A, B bar, okay, 1, and then the rest will be X. So we can have all here in one loop. So JB equal to 1. Okay, remember I told you when we can have a loop considering all the elements in the kind of map, so the answer is 1. Okay, then the last one for KB, KB also 1. Okay, so next you have the expression, 4 expression for JA, KA, JB, KB. Next step, you can draw. Okay, this is the basic element to flip-flop. Okay, JK, the clock, and then Q bar, set, clear. And then for 1, you just drag the wire from J and also from K, put 1 here because KB and JB both 1. And then this is the flip-flop for B, so you drag 1 wire from the Q of the second flip-flop, connect it to B. And then this one is flip-flop for A, so this is the input, so drag 1 wire from Q, connect to A. And then for JA, the input here is B. Okay, so B, input for J is B, so drag 1 wire from B goes into J for flip-flop of A. And then for KA also okay, KA equal to B, so drag another wire here, go to KA. Okay, then you have to connect the clock of both flip-flop to the clock signal. So that's how you answer this type of question, synchronous counter design.